Unit 4 Chemistry, Chapter 17, Part 2. Now we're looking at how we can measure these energy contents. Right. And we measure them by a process called calorimetry. So we remember our enthalpy changes from way back at the beginning of Unit 3. Okay? Enthalpy is the energy in a reactants compared to the energy in the products. Okay? And we can measure that change in energy using a calorimeter. A calorimeter is a reaction vessel, essentially, and we contain the reaction in a vessel that contains water normally. We can do it with gases in what's called a bomb calorimeter. The reaction heats or cools the water, and we record the temperature change. And we use that temperature change to calculate the amount of energy released or taken in. Now you might think, hang on a minute, you're just doing it using specific heat capacity here. Sort of. What we're actually doing first is we're calibrating our calorimeter. Okay? When we use specific heat capacity, we don't take account of how much energy is absorbed by the reaction vessel or lost to the environment. What we do first in calorimetry is find out how much energy does it take to raise this reaction vessel by 1 degree, and then we use that. So, this would be an example of a solution calorimeter. Okay? And in some cases you might keep your reactants separate so we don't have to take the lid off. Yours won't be quite that sophisticated when you come to use them. Or we can do it in a bomb calorimeter and then we have the water around the outside. First thing we always do is calibrate it. Okay? The most common way of calibrating it is using electrical current, though we can use a known reactant. Okay? So we add via electrical current a set amount of energy, which we measure by measuring the voltage, the current, and the time. When you multiply the voltage, the current, and the time, that gives you the energy in joules. We then take that energy and divide it by the change in temperature of our water. So energy is divided by delta T, and that gives you a calibration factor in joules per degree C. Okay? That tells us how much energy we need to raise the temperature of that calorimeter by 1 degree. We can then use that calibration factor to find out how much energy actually was transferred in our reaction. So we take our calibration factor and we multiply it by delta T of our reaction. So in that same calorimeter that you just calibrated, you now do a reaction, you're going to get a second change in temperature, and you multiply that by the calibration factor. And that tells us how much energy was released in that reaction, or taken in. You then divide that by the amount in mole of your limiting reagent, and that will tell you your delta H per mole. And it will give you a delta H per 1 mole, so check that when you're writing a thermochemical equation. Remember, thermochemical equation, the delta H value has to agree with the number of mole that you've got in your equation. So if in your equation you've got 2 moles of your limiting reagent, double that delta H value before you write it down. If you've got 3 moles, triple it. Okay, check your coefficient. And then remember that if the temperature went up, the reaction was exothermic. So you're now going to artificially write in a negative sign. It's not going to come out in your calculations. You're going to think, ah yes, exothermic, negative. If it's positive, if the temperature went down, it was a positive delta H value, and you must put in that positive. Don't just leave it out and say, oh, that'll mean positive. It just means you forgot the sign. So our temperature changes in calorimetry, we'll see it may go up, it may go down, but the difference between the start and the end temperature is our delta T. Doesn't matter whether that's in degrees C or Kelvin, because it's just a difference. Okay? It will reach a peak temperature. It will then start to slowly decrease. The peak temperature, that's what we need to be measuring, because we're going to start losing some heat to the environment.